Pharmaceutical chemistry is an exercise in isolation. When synthesizing a new drug, the reaction produces a complex mixture of synthetic byproducts. The first challenge is isolating a specific target molecule from that dense mixture. To do this, we rely on physical separation. We have to physically strip away the unwanted chemical materials to isolate the pure compound. Once separated, we have to prove exactly what we made. We must determine the precise molecular structure, identify the functional groups, and measure the exact mass of the target compound. This is characterization. Historically, these two steps operated as discrete, disconnected processes. You run your mixture through a separation column, and the analytical pipeline comes to a dead stop. To characterize that separated sample, a scientist has to manually extract it, carry it across the laboratory, and physically re-inject it into a different machine. This manual transfer costs time. It consumes limited sample volumes and exposes sensitive compounds to atmospheric contamination. As long as separation and characterization exist as strictly physical islands, the pace of drug discovery is restricted by the speed and risk of manual labor. The solution to this bottleneck is a structural engineering intervention known as hyphenated techniques. The concept relies on directly and physically coupling a separation instrument to a spectroscopic detector. This hybridization eliminates the physical gap between steps. The dead stop is replaced by a continuous pipeline. This enables real-time processing. Separation and detection happen sequentially on the exact same sample injection, without human intervention. Hyphenation optimizes analytical chemistry by turning discrete laboratory tools into an automated, unified engine. Mastering hyphenated systems does not require learning new underlying scientific principles. These systems are built on a modular, plug-and-play architecture, using established tools you already understand. The first module is the separation block. Let's use gas chromatography, or GC. In GC, a carrier gas segregates a volatile mixture by pushing it through a column. Components separate based on their varying retention times inside that column. The second module is the characterization block. We will use mass spectrometry, or MS. Mass spectrometry ionizes and fragments molecules to deduce their exact mass and structural blueprint. Notice the physical gap between the GC exit port and the MS entry port on our mental workbench. If you understand how the individual modules work, you only need to understand the bridge connecting them to master the entire machine. That bridge is the interface. It is the critical engineering variable in hyphenated techniques. The interface has one strict mandate: environmental continuity. The transition pathway must guarantee zero sample deterioration between machines. This is a significant physical challenge. In a GC-MS setup, the gas chromatographer operates at atmospheric pressure, while the mass spectrometer requires a high vacuum. The interface perfectly bleeds off excess GC carrier gas while transferring the isolated sample into the MS vacuum. It also solves a thermodynamic threat. The volatile sample must remain a gas, requiring the transition tube to be wrapped in a precisely controlled thermal envelope. If the interface temperature drops even slightly, that volatile sample condenses, collapsing back into a liquid inside the transition tube. Condensation or chemical degradation during transit makes the hybridization ineffective. The viability of a hyphenated system depends on the thermodynamic precision of its interface pathway. Once the interface logic is engineered, the system becomes highly adaptable. The initial gas separation module can be swapped out for liquid chromatography, or LC, and the mass spectrometer detection module can be swapped out for nuclear magnetic resonance spectroscopy, creating an LC-NMR system. The central interface simply adapts to the new physical constraints, routing continuous liquid eluent directly into the magnetic resonance chamber. This modularity grants chemists the ability to configure specific instrumental pairings for a wide range of molecular structures. Let's track a real-time operation of a coupled system from start to finish. A single droplet of a complex mixture is injected into the closed hyphenated pipeline. Inside the first module, that physical sample sequentially separates into isolated bands. Those isolated bands pass immediately through the protected interface, directly into the detector. This split-screen visualization shows the data output, a multi-dimensional graph combining separation time and structural mass. The top half displays a standard 2D chromatography, mapping separate bands as distinct peaks. Every peak instantly outputs a corresponding structural blueprint in the mass spectrum beneath it. We achieve physical separation and precise structural elucidation at the same time, from the same injection. The primary operational advantage is a measurable reduction in total analysis time. Economically, it maximizes the conservation of rare or expensive sample volumes by eliminating manual transfer. It also ensures strict data integrity, protecting sensitive, easily degradable compounds within a sealed environment. Automating the transition between instruments maximizes the data yield of every injection, while protecting the physical integrity of the sample. By merging the physical resolution of chromatography with the analytical depth of spectroscopy, these systems optimize the analytical pipeline and the speed of scientific discovery.